friend, welcome to this lecture. In this lecture we will continue our study of stability of nonlinear system. If you recall, we in previous class we have defined what do we mean by stability of a solution of a nonlinear system. For example, if we have a say x dash equal to f dx, x dash equal to f dx, and we have a solution like x equal to phi t, then we say that this phi t is a stable solution provided that if we take any other solution psi t of x dash equal to f dx such that initially, let us say the initial point is t naught is the initial point where this differential equation is start functioning, or t naught is some initial point such that this phi t naught minus psi t naught is less than some very small quantity, call it delta. And so, if we take any other solution psi t such that this norm, this is basically norm of phi t naught minus psi t naught is less than delta, implies that norm of phi t minus psi t is less than some epsilon. So, it means that for I can call this as for every epsilon greater than 0 there exists a delta greater than 0, of course it is depending on epsilon, such that this quantity is true, means norm of phi t minus psi t is less than epsilon whenever they are near to say whenever norm of phi t naught minus psi t naught is less than delta. So, if for every psi t we have this condition true, then we say that x equal to phi t is a stable solution of x dash equal to f dx. So, this is how we have defined the definition define the stability of a given solution. Now, let us focus on a particular case of this, when let us assume that f dx is simplified and we can write it like a of x. So, it is an autonomous system. So, now x dash equal to in place of f dx we are considering a particular special case of this, that is x dash equal to a x. It means that we are considering that f dx is given by a of x, and then we try to get some condition on say coefficient matrix A such that the every solution of x is stable or unstable or say half stable, something like that. So, let us try to find out the condition on the coefficient matrix A such that we can talk about the solution of this linear system x dash equal to a of x. So, now let us move to this. So, let A be a real matrix of size n cross n matrix. The stability of any solution of the linear autonomous differential equation x dash equal to a of x, and this may be defined by, this may be determined completely as we have methods available to find out all the solution. We have already discussed the method to find out the complete solution of x dash equal to a x, and once we have complete solution of x dash equal to a x, we can find out the behavior of its solutions. So, it means that we have methods available to find out all the solution of a given linear system, and in this we can discuss the stability of any solution of x dash equal to a x in complete manner. So, in this regard we have following two remarks, and first remark is that any solution of a given linear system x dash equal to a x is stable or unstable if the equilibrium solution x t ideally equal to 0 of the linear system is stable. So, it means that what this remark 1 says, that if x t ideally equal to 0 is stable, then any solution is stable, and vice versa, means if any solution of a given linear system is stable, then 0 solution is also stable. So, it means that here the stability behavior is equivalent whether it is any solution or a 0 solution. So, it means that 0 solutions will give you the stability behavior of any solution. So, if 0 solution of linear system is stable, then any solution of linear system is stable, and if 0 solution of linear system is unstable, then any solution of the linear system is also unstable. So, this is the first and very important remark. Now second remark is that since here we have to calculate n quantities, because we are talking about that this phi t minus psi t is near. So it means that we have and we are assuming that phi t and psi t are column vector function of size n cross 1. So it means that we have to check that n quantities like size a t I equal to 1 to n are small if we are taking considering the stability of 0 solution. Then we have to check that norm of psi t is less than epsilon. On this implies that every component like psi j t is less than epsilon for every j equal to 1 to n. So rather than checking for n quantities psi j t, we have to we will use, not we have to, we are using one different form of norm. Here we are taking this norm which is known as maximum norm. So here we simply take norm of psi t is equal to maximum of modulus of psi 1 t and modulus up to modulus of psi n t. So here we are using the supremum of say maximum of each psi I t, and then we call this as norm of psi t. So if we are using this, then we can establish our result only in terms of this norm, and if it is true for this norm, then it means that each psi I t is less than epsilon, and hence we can have the required result. So first let us check the first one, the let us verify this remark 1, and it says that you look at here, we simply say that we have a system x dash equal to a of x, and we say that if x t ideally equal to 0 is stable solution, this implies that any solution of x dash equal to a of x is also stable. So let us take in particular, let us say any solution, let us take phi t as one of the solution, and we want to say that if x t ideally equal to 0 is stable, then we want to check that phi t, which is a solution of x dash equal to a x, is also stable. Now we already know that in case of homogeneous linear system, we already know that if phi t and psi t are any two solutions of x dash equal to a of x, then phi t minus psi t is also a solution of x dash equal to a x. That is what we already know, that even this solution set forms a vector space, right. So for x dash equal to a of x. So it means that if phi t and psi t are any two solution, then their difference is also a solution of x dash equal to a of x. Now let us say that 0 solution is stable, means we simply say that if you take any other solution, let us call it z t. So 0 minus z t is less than epsilon whenever it is for every epsilon greater than 0 they exist a delta greater than 0, such that this 0 minus norm of 0 minus z t is less than epsilon whenever 0 minus z t naught is less than delta, where z t is any solution of x dash equal to a of x. Now since z t is any solution, and we already know that if phi t is a fixed solution of x dash equal to x, for which we want to find out the stability criteria, and let us say that psi t is any solution. So fix phi t and psi t is any solution. So it means that if psi t is an arbitrary solution of x dash equal to a of x and phi t is a fixed solution of x dash equal to a of x, then we can say that phi t minus psi t is also an arbitrary solution of x dash equal to a of x. So in particular I can take the expression z t as phi t minus psi t. So it means that this I can rewrite as 0 minus z t is nothing but z t. So I will write phi t minus psi t is less than epsilon whenever norm of phi t naught minus psi t naught is less than delta. So, it means that for every epsilon greater than 0 there exists a delta greater than 0. So, the norm of phi t minus psi t is less than epsilon whenever norm of phi t naught minus psi t naught is less than delta. Now, if we look at this carefully, and if we take phi t as the fixed solution for which we are searching for the for which we are looking at the stability behavior, then this simply says that for every epsilon greater than 0 there exists a delta greater than 0 such that norm of phi t minus psi t, where psi t is any solution of x dash equal to a of x, is less than epsilon whenever norm of phi t naught minus psi t naught is less than delta. So, we can say that in this way phi t x equal to phi t is a stable solution. So, this we are getting when we are assuming that 0 is a stable solution. So, this implies that if 0 is a stable solution, then phi t, where phi t is any fixed solution of x dash equal to ax, is also a stable solution. Now, we want to prove the other way around. We simply say that if 0 is unstable, if x ideally equal to 0 is an unstable solution, then we want to prove that any solution, let us say phi t, is also unstable. So, how we can look at? So, if x equal to 0 is an unstable solution, it means that they exist, say a solution H t of x dash equal to a of x such that the 0 minus h of t. So, for every epsilon greater than 0 they exist a delta. I can find out that we have a solution H t such that norm of 0 minus H t is greater than epsilon for every delta such that h of t naught is less than delta. So, it means that for every delta you can always find out one epsilon such that norm of 0 minus S t is greater than epsilon whatever delta I will choose. So, it means that I can always, so it means that they exist an epsilon greater than 0 such that norm of S t is greater than epsilon for every delta such that norm of S t naught is less than delta. So, it means that, or we can write it like this, that h of t is one such solution such that it is near to 0 at t equal to t naught. So, at t equal to t naught this norm of S t is small, S t naught is less than delta, but as t is greater than say t naught, then that norm of H t is going to be bigger than some pre-assigned number. So, it means that we can say that H t is now moving away to this 0, right. So, that is what do you mean by an unstable solution. Now, we want to show that this phi t is also unstable. For that we simply consider one solution psi t as phi t plus this H t which we have taken here. So, if we take psi t, and since H t is one such solution and phi t is already we know, then psi t is one solution of x dash equal to a x such that norm of phi t naught minus psi t naught, which is nothing but h of t naught, we already know that this is less than delta, but this also implies that norm of phi t minus psi t, which is nothing but norm of h of t, and it is bigger than some epsilon. Let us fix that epsilon. So, it means that if we take let us call this as epsilon naught here. So, it means that they exist epsilon naught greater than 0 such that norm of H t naught is less than delta is true, but norm of H t is always bigger than this number epsilon naught. So, it means that if I take epsilon less than epsilon naught, then the previous condition does not hold true. It means that for epsilon which is less than epsilon naught, I cannot find out any delta such that norm of Z t is less than epsilon whenever norm of ZT naught is less than delta, because this norm of HT is always bigger than this epsilon naught. Is it okay? So, it means that for the same epsilon naught, we can simply say that we can find out a solution psi t such that psi t which is given as phi t plus h of t. It means that for this epsilon which is less than this epsilon naught, I cannot find out any delta such that norm of ST naught is less than delta, implies that norm of ST is less than epsilon, right, because this norm of ST is always bigger than this epsilon naught. So, it means that if 0 solution is unstable solution, then this implies that phi t is also unstable solution, and this is very important result in the sense that rather than checking the stability of any solution, we will just check the stability of only 0 solution, right. So, it means that if we simply check the 0 solution is stable, then we say that any solution is unstable stable, and if 0 solution is unstable, then we simply say that any solution is unstable. So, keeping this thing in mind, let us consider the following theorem, which gives you a complete description of stability of 0 solution, or we can say stability of any solution, because the stability of 0 solution is equivalent to stability of any solution of x dash equal to a of x. So, now let us look at the theorem. It says that every solution x equal to phi t of 1 is stable if all the eigenvalues of A have negative real part, and so it means that if you calculate eigenvalues of A, and it may be real, it may be complex, but in any case the negative real part, whether it is purely real or a complex value, if the real part for all the eigenvalues are negative, we simply say that solution is stable, 0 solution is stable, and hence any solution is stable. Second part of this theorem says that every solution x equal to phi t of 1 is unstable if at least one eigenvalue of A has positive real part. So, it means that if any of the eigenvalues of A have one positive real part, a positive real part, then the solutions are all unstable. So, all solutions are unstable solution. So, the first part deals with the negative real part. If all these eigenvalues are having negative real part, it is done, we have concluded that every solutions are stable solution. Now, the second part says that if at least one of the eigenvalues have positive real part, then all the solutions are unstable solution. And the part C says that if we have some eigenvalues with 0 real part, then what we need to consider. So, C part says that suppose that all the eigenvalues of A have real part less than or equal to 0, because if it is any of the eigenvalue have positive real part, it is all unstable. So, there is no question arise when we have one eigenvalue with positive real part, then we have one certain answer that it is unstable solution. But if we have, say, consider that all the eigenvalues of A have non-positive real part, and let us say that we consider few eigenvalues with 0 real part. So, let us say that lambda 1 is I sigma 1 and lambda L equal to I sigma L. These are some eigenvalues with non-zero real part, 0 real part. So, let lambda j equal to I sigma j have multiplicity kj. So, in the case when real part is 0, then we have to look at the algebraic multiplicity and geometric multiplicity. So, if we say that if algebraic multiplicity is kj, it means that lambda j is repeated root of characteristic equation of multiplicity kj, and the characteristic polynomial of A can be factored into this form that P lambda equal to lambda minus I sigma 1 to power k 1 into lambda minus I sigma L k L q lambda. So, where q lambda have all the roots having negative real part, right. Then in this case every solution x equal to phi t is stable if A has kj linearly independent eigenvector for each eigenvalue lambda j equal to I sigma j. Otherwise every solution is unstable. So, please try to understand here, in first part all the eigenvalues are negative, right. So, having negative real part. In second it is positive, at least one with positive real part. Now consider equality one side, let us say equality is here, because if we have equality here then we know that all solutions are unstable. So, there is a possibility here that solution may be stable, may not be may not be stable. So, here we consider the case when equality appears. So, it means that there are eigenvalues for which we have 0 real part. Okay. So, now let us say that your lambda 1 to lambda L are eigenvalues with 0 real part. Then we have to look at the algebraic multiplicity of say lambda j and geometric multiplicity of lambda j, right. If it is equal for each j, right, then we say that solutions are stable solution, otherwise solutions are unstable. So, it means that if for all j algebraic multiplicity of lambda j is equal to geometric multiplicity of lambda j, then solution are stable, and if there exists one j such that this is not equal, it means that am lambda j is not equal to gm of lambda j, then all the solutions are unstable solutions. So, this is the content of this theorem. In fact, here stability of any solution of x dash equal to Ax is now purely depending on the behavior of eigenvalues of the coefficient matrix A. So, that is that gives a very important result in terms of the eigenvalues of the coefficient matrix. Now, let us try to prove this. So, first let us prove the first part A, that all the eigenvalues have negative real part. So, first thing we need to observe that every solution of 1 with initial condition x of 0 equal to psi 0 can be written as psi of t equal to e to power a t into psi of 0, and this we can done in the sense that when we have say solution x dash is a differential equation x dash equal to a of x, we already know that e to power a t will serve as a fundamental matrix solution, and any solution of this equation x dash equal to a x can be written as e to power a t into c. Let us call this as x t. So, x t can be written as e to power a t into c. Now, depending on the initial condition we can fix this constant matrix, that is c. So, now let us consider the initial condition x of 0 equal to psi of 0, then we can denote this particular form of the solution is given by psi t is given by e to power a t psi of 0. Now, so this any solution with the condition x of 0 equal to psi 0 is having this form, that psi t equal to e to power a t psi of 0. Now, we want to look at how the stability of this psi t is depending on the eigenvalues behavior of the eigenvalues of A, matrix A. So, let Bijt be the ij element of the matrix EAT. So, we have EAT is like a matrix of say solutions. It means that every column of e to power a t is a solution of x dash equal to a of x. Not only this, that each columns, in fact x1 to xn's are linearly independent solution of x dash equal to ax. Okay. Now, let us say that psi 1 0 to psi n 0 be the component of psi naught. Now, we want to look at this psi t equal to e to power a t psi 0 in terms of component. Okay. So, here let me write it, this is the matrix Bijt, and psi 0 I am writing psi 1 0 to psi n 0. So, it is something like this B 1 1 t to b1nt, and here it is bn1t to bnnt, and here we have psi1 0 to psi n 0, okay, and this is your psi 1t to psi nt. So, it means that if we looking at the ith component, then I can write out psi it as the ith row multiplied by this. It means that I can write psi it as bi1t into psi 1 0 plus bi2t into psi 2 0 and so on bint psi n 0, or I can write it like this j equal to 1 to n bijt psi j 0. Now, we already assume that all the eigenvalues of A have negative real part, and hence we can find out the largest of the real part of the eigenvalues of A. So, it means that suppose negative real part means suppose they have say lambda 1 minus lambda 1 minus lambda 2 and so on minus lambda n. Here I am assuming that lambda I are positive. So, we have these, you just arrange in this, so somewhere here it is 0 and somewhere here we have lambda n and somewhere we have lambda minus lambda 1. So, let us look at the nearest to 0, that is call it minus alpha 1, we denote it like minus alpha 1. So, whoever be it may be anything. So, let us say that minus alpha 1 is the largest of the real part of the eigenvalues of A. So, it means that it may be real or it may be complex. Just look at the real part of the eigenvalues of A, and let us say this minus lambda 1 denote the real part of the eigenvalues lambda 1. Let me use some other notation, let us use it lambda 1 tilde lambda n tilde. So, these are the real part, we are looking at the real part. So, let us say that minus alpha 1 be the largest of the real part of the eigenvalues of A, right, or in terms of if we want to look at in terms of the absolute value, then look at the absolute value here lambda 1 tilde and lambda n tilde, then this alpha 1 will be the smallest absolute value corresponding to the smallest absolute value of the real part of the eigenvalues of A. So, now corresponding to this minus alpha 1, let us choose one more number say alpha such that minus alpha 1 is less than minus alpha less than 0, right. So, first thing is we have all the eigenvalues, arrange it in this manner, arrange the real part of eigenvalues in this manner and choose the greatest largest real negative real part as minus alpha 1, and corresponding to this minus alpha 1 find out one more number minus alpha such that minus alpha 1 is less than minus alpha less than 0. So, here you choose somewhere here your minus alpha, right. So, it means that now corresponding to this minus alpha, our claim is that I can find out a number k such that bijt is less than or equal to k e to power minus alpha t for t is greater than or equal to 0. That is very important observation in the sense. Now, if you look at that e to power at is a matrix of this form. So, it means that the first column is b11t, b21t and so on up to bn1t. Now, it may happen that we have eigenvalues like we have n eigenvectors, then this is nothing but some constant times some e to power some lambda 1 or lambda 1t, but it may happen that we may not have n linearly independent eigenvectors. Then first or any of the column this of e to power at may be say of this form like qt times e to power lambda it, let me write it like this qit lambda e to power lambda it, where this qit is a polynomial in terms of t and whose degree is at most n minus 1, it cannot be more than n minus 1. So, it means that the at most the degree of the polynomial is n minus 1 and into e to power lambda it, and it is it will achieve the degree n minus 1 in the case when we have only say eigenvalues lambda I up to say repeated n times, and for example if you have say identity matrix 1 1 1 1. So, in this case we have only one root, that is 1, and it is repeated n times. In this case here it is diagonalizable, it is quite obvious, but if we look at the Jordan block corresponding to 1 1 of size n, then we can we have only one eigenvector, rest are all generalized eigenvector, and the solution will look like this, and let me write it here. Solution will look like what? Solution corresponding to is looking like e to the power lambda I t, and here it is u, that is eigenvector, plus a minus lambda I t into v, I can write it v here, no problem, plus a minus lambda I square t square upon factorial to v, and so on up to a minus lambda I power n minus 1 t to the power n minus 1 upon factorial n minus 1 v, right. And this I am calling as, we can arrange this and I can write this as q I t e to the power lambda I t. We rearrange in this manner, and we can write it like q I t e to the power lambda I t, I can write it like this. So, it means that the each column, let me write it here, x I t is of this form, and maximum degree of this polynomial is going to be maximum n minus 1. So, degree of q I t is less than or equal to n minus 1. Okay, so, if it is happening, and then we can say that q I t e to the power lambda I t, and it is less than, I can write it k e to the power minus alpha t. So, our claim is that since it is true for since this alpha minus alpha is bigger than minus alpha 1, it is less than 0. So, my claim is that I can always write norm of e to the power a t. In fact, I can write it like this, that norm of bij t is less than k e to the power minus alpha t. So, how I can write it here? My claim is that I can find out one k such that q I t e to the power lambda I t modulus of this, norm of this is less than k e to the power minus alpha t. So, how we can say, this I can achieve like this, that q I t e to the power lambda I t divided by e to the power alpha t, right, and take limit t tending to 0. So, this I can write it here is equal to norm q I t e to the power, this will go lambda I minus alpha t, and it is tending to 0, sorry, t tending to infinity. Now, if you look at what is lambda I minus alpha, lambda i's are say if we are looking at the norm here, then it is less than or equal to norm of q I t into norm of e to the power, in fact it is modulus of e to the power lambda I minus alpha t, right. Now, here look at the sign of lambda I minus alpha. So, lambda I is less than minus alpha 1 and it is less than minus alpha less than 0. So, lambda I minus alpha will be negative, right. So, it means that if it is negative and as t tending to infinity, this will go to 0, and since exponential function is dominating function over the polynomial, I will say that this limit will tend to 0 as t tending to infinity. So, if it is tending to infinity, I can always find out a function k such that norm of bit is less than k e to the power minus alpha t. That is what we have written here, that bijt is less than or equal to k e to the power minus alpha t, t greater than or equal to 0. This we can always do this. Let us again work on this, and this is true. So, you can consider this as an homework and let us relook at it. Therefore, norm of psi I t is less than or equal to j equal to 1 to n. Now, b I j t is bounded by k e to power minus alpha t. So, we are writing this as k e to power minus alpha t norm of psi j 0, and this is k e to power minus alpha t summation j equal to 1 to n psi j 0 for some positive constant k and alpha. Now, we already know that this psi j 0 is less than or equal to norm of psi naught. Here norm of psi naught is basically maximum of psi j 0, j is from 1 to n. So, each one is less than or equal to maximum of psi j 0, which I am denoting as psi j 0. So, this is less than equal to psi, each one is less than or equal to norm of psi 0. So, in place of this I can write it here that norm of psi I t is equal to maximum of psi 1 t to psi n t, and we already know that for each psi I t it is less than or equal to n times norm of psi naught 0 k e to power minus alpha t, and it is true for each I. So, in particular the maximum will also be less than n k e to power minus alpha t norm of psi 0, right. So, it means that psi I t is less than this. Now, e to power minus alpha t is always less than 1, right. So, I can write this that norm of psi I t is less than or equal to n k into norm of psi 0. So, now you can choose delta, since delta we have to choose. So, given any epsilon we have to choose delta such that norm of psi I t is less than epsilon whenever psi I t naught is less than your delta. So, now choose delta as epsilon by n k, right. So, that norm of psi I t is less than epsilon if norm of psi 0 is less than delta epsilon at t naught and t is greater than or equal to 0. Here t naught I am choosing as 0 here. So, it means that norm of psi I t is less than epsilon whenever norm of psi t naught, here it is 0, is less than delta, and hence we can say that the equilibrium solution x of t ideally equal to 0 is stable. So, we have shown here that if all the eigenvalues have negative real part, then I can find out minus alpha in a way such that norm of b I j t is less than k e to power minus alpha t, and with this we try to find out the bond of norm of psi I t, and hence we can show this thing that norm of psi I t is less than epsilon whenever norm of psi 0 is less than delta, and this shows that the 0 solution is a stable solution, and if 0 solution is stable we have already shown that any solution of x dash equal to a x is also stable, and so it means that if all the eigenvalues of A has negative real part, then 0 solution is stable, and hence every solution of x dash equal to a x is a stable solution. So, with this I stop our discussion, and in next lecture we will discuss the its second and third part, and then we will also discuss some nonlinear system of differential equation, and we will discuss the stability of solutions of nonlinear system. With this I stop, we will continue in next lecture. Thank you very much for this.